Hey class, this is Mr. Albert, Shasta High School, and I'm coming to you from the garage. We went over these problems in class on Friday, but I realized some of you are absent, and that had to be fast because it had to happen within a class time. So I'm going to go through these problems a little bit slower, and if you feel like you're struggling, it would be really well worth your time to kind of spend some time going through these and consider what's happening here. Um, so let's take a look and get started. The first series of problems asks us to simplify some monomials, and we're advised that, our final answer cannot contain compound fractions. That's fractions within fractions, right? That's not considered simplified form. Our answer should not contain fractions mixed with decimals. Our answers may not contain negative exponents. So with all those restrictions and caveats, like we gotta know exactly how to rewrite these things so that they don't have any of those things. The first thing I want to look at here is that I have x to the third divided by x to the negative third. Those are not the same, right? This is not x to the third over x to the third, which would be a giant one. It's x to the third over x to the negative third. We know shortcuts for dealing with negative exponents, but the justification for those shortcuts always comes down to the fact that I'm always allowed to multiply a fraction by the number one. And if I multiply something by one, it doesn't change what it is. It might be used to just change its format. So what I'm going to do is I'm going to multiply by the number one, but it's going to be constructed in such a way so that when I multiply by the number one, it's going to get rid of this negative exponent. So what I'm going to do is I'm going to multiply the denominator by x to the positive third power. I'm picking x to the positive third because I know that if I have x to the negative third times x to the positive third, that would be x to the 0 power. And x to the 0 power would equal the number 1. So it's going to make the negative exponent cease to exist on the denominator. Now, again, I can't multiply by anything other than the number 1, right? So I make this the number 1 by putting an x to the third in the numerator. So here's what we have. In my denominator, I've got x to the negative third times x to the positive third, which equals what? X to the 0, which is 1. So when I look at this now, I no longer have a negative exponent, right? So I'll just rewrite what we have. Where we're at right now is this is now 30, not 3x, but it's 35x to the 6th power, right? I've got 1, 2, 3, and 1, 2, 3. There are 6 factors of x over the number 21. One more thing that's possible here, right? The negative exponent is gone. That's simplified. The other thing that's possible that there is a common factor, right? Both 35 and 21 have a common factor of 7. If I choose to, I can write, hey, this is 5 times 7 over 3 times 7, right? So this is, what I've just written is 35 over 21, but you can clearly see that there's this common factor of 7 over 7, the giant 1 there. So it's now gone. So what my final answer is in my numerator, I'm going to have 5 times x to the 6th power. And in the denominator, there's just this single factor of 3. Again, there's the 5, there's an x to the 6th, and then there's that 3. Okay, let's go to question part B. Same question, question 1, part B. Okay, so on this one, first things first, I observed that some of us think that the 2 is being squared in this expression. And let's be real clear, that is not 2 being squared. That's just 2 times an x times another x. That's 2x squared. So we are not looking at this. This is not 2x in parentheses squared, and then that's being raised to the 3rd power. That's not what we have. We just have 2xx, right? So in the parentheses here, there's a 2 and an xx, or 2x squared, and I have exactly 3 of those. So if I want, I could simplify by writing that out or expanding it out. So I've got 2x squared times another 2x squared times another 2x squared. Now, that's part of it, but then also I have this times 4x. So if I'm looking what I've got here, this is a 2 times a 2, which is 4, times a 2, which is 8, times the number 4, which would be 32. So the coefficient part is the number 32. And how many factors of x do I have? Well, there's 1, 2, 3, 4, 5, 6, 7 of them. So my answer here is 32 times x to the 7th power. I'm not going to write that down on the answer space over there, but you can see this is 32x to the 7th power. For part C, we do have 2, and then that's being multiplied by x to the negative 5th. Again, it's kind of a common error that I'm seeing. This is not 2x to the negative 5th, right? So the 2 is not being raised to a negative exponent, right? That negative to the negative 5th power does not apply to the 2. So if I'm going to look at this, I'm going to follow my protocol for getting rid of a negative exponent. I'm going to multiply by the value of 1 that will eliminate this negative exponent. So in my numerator, I'm going to go ahead and multiply by x to the positive 5th power. Why did I pick that? Because I know that these two together, right, are going to make x to the 0, which would equal 1. So I no longer will have that negative exponent. Now I can't leave it there, right? I have to match that and put 5 factors of x in the denominator here. So again, I can always multiply by 1. That's exactly what I'm doing. When I multiply by 1, in this case, I make this becomes the number 1, right? So that's 2 times 1 is in my numerator, and in my denominator, I have x to the 5th. So my final answer would be 2 over x to the 5th power. And then the final question in question 1, part D. This does have a couple different negative exponents. I could deal with all the negative exponents immediately if I wanted to, but I'm noticing that the factors of a are going to kind of take care of themselves in the numerator first. So I'm going to deal with that. In my numerator, I've got right here, I've got 7 factors of a, right? That's a times another a. So there's a to the 7th power. And I'm multiplying that by a to the negative 4th. So that's going to reduce the factors of a I have by 4. So that's going to make this entire numerator just become a to the 3rd power. So I'm just going to go ahead and write that now. There's an a to the 3rd in the numerator. In my denominator, I have a 5 to the negative 1 and a b to the negative 2nd power. So same thing I'm going to do is I'm going to multiply again by the number 1 to eliminate these negative exponents. So I'm going to do it actually twice. I'll do it once on this side and once over here on this side. On the right-hand side, on this side, I'm going to multiply by b squared. Again, why b squared? Because I'm mirroring this. I'm getting the opposite of that. B to the negative 2nd times b to the 2nd gives me b to the 0. And I'm going to match that by putting b squared up in the top. Same thing with the 5. I've got 5 to the negative 1, so I'm going to multiply by 5 to the 1st in both the top and the bottom. And again, all I'm doing is I'm multiplying by the number 1 2 times. 5 over 5 is 1, b squared over b squared is 1. So I'm not changing the value of this expression. I'm just changing its format. What I'm left with is this is 5 to the 0, which is 1. This is b to the 0, which is 1. So my numerator now is just 1 times 1. That's my denominator, rather, is a 1 times 1. This is 1, this is 1. 1 times 1 is 1. In the numerator, I've got 5 times a cubed times b squared. So this is the numerator that I'm left with, 5 times a cubed times b squared. So let's continue to question number 2. As I look at this, I'm going to begin with a rewrite of the left-hand side. And I'm going to multiply both of these terms that are inside of the parentheses by the number negative 2. So this left-hand side is going to become negative 10x plus the number 2. Because negative 2 times negative 1 would be positive 2. And over on the right-hand side, I've got negative 58 plus 10x. So that was just a rewrite of the left-hand side only. The next thing I'm going to do is add 10x to each side. So if I was to add 10x to each side, this left-hand side is now just going to become the number 2. It was a negative 10x, but since I added 10x, that's negative 10x plus 10x is 0. So now the left-hand side has the number 2. The right-hand side has a negative 58 plus 20x. Next, I'm going to add 58 to each side. Add 58. When I add 58 to the left-hand side, I get the number 60. And when I add 58 to the right-hand side, I'm just going to get positive 20x because negative 58 plus 58 would be 0. And then as a final step, I'm going to divide both sides by 20. 60 divided by 20 is 3. And 20x divided by 20 is x. So my answer here is that x is equal to 3. The problem does say, make sure you verify that your answer is a solution before you move on. And I'm going to demonstrate that at least with this simple one so that you're clear what that looks like. So let me turn on the calculator here. If I was to verify this solution, I might take the number 3 and store that as x. So now my calculator believes that x is 3. If I ask it, hey, what's x? It says it's 3. And I'm going to type in the original left-hand side and right-hand side and confirm that those two sides become the same when x is 3. So over on the left-hand side, this becomes negative 2 times the quantity of 5x minus 1. So the left-hand side becomes the number negative 28. Let me write that down. So on the left, I've got negative 28. And the question, is that the same as the right-hand side? The right-hand side, I would type negative 58 plus 10x's. And 10x, and when I press enter, it says that's also negative 28. So when I say confirm that you have an answer, this is confirmation, right? This is why this is a check. It's a check because both the left-hand side and the right-hand side are the same. They are both negative 28 when x is 3. So that is our solution. So we can write down that x is the number 3. Let's go to part B. Again, I'm going to do a rewrite on the left-hand side. I'm going to rewrite this as negative 2x and then plus the number 6. And then minus 4x. And on the other side, this is negative 8x plus 14. And sometimes I like to write down that what did I do? I just did a rewrite. And the only thing I rewrote was the left-hand side, so I might put L. Next, what are we going to do? I'm going to do a rewrite on the left-hand side again. So I've got negative 2x and negative 4x, which would be negative 6x plus 6 is negative 8x plus 14. And again, that is another rewrite of the left-hand side only. Now I'm going to start doing things to both sides of the equation. And the thing I'm going to choose to do first is I'm going to add 8x to each side. When I add 8x to the left-hand side, this is going to become 2x plus 6. And when I add 8x to the right-hand side, it will become the number 14. Next, I'm going to subtract 6 from each side. 14 minus 6, I believe, is the number 8. So this is going to become on the left-hand side 2x, and on the right-hand side 14 minus 6 is 8. And then as a final step, I'm going to divide both sides by 2. So that's going to give me that x is the number 4. Okay, so again, I believe x is the number 4. I'm going to tell my calculator that x is something different. I'm going to say, hey, 4 is what x is now. So now my calculator believes x is 4. and I want to ask it to evaluate the original left and right hand side. So I type negative 2 times the quantity of x minus 3, and then I'm going to subtract from that 4x minus 4x. And I get over on the left-hand side negative 18. I'm going to write that down. And the question is that the same as the right-hand side? On the right-hand side, I have negative 8x and then plus 14. And when I press enter, that also says negative 18. So it is definitely the case that when x is 4, both the left-hand side and the right-hand side are the same. That's why this is called a solution to the equation, right? It forces both the left and right-hand side to become the same number. So x is 4 as a solution. All right, the next two involve fraction busters. And, I did these in class, but I had to do them kind of faster, quickly. So I'm going to go a little slower here, give you an opportunity to see this maybe better. When I look across my denominators here, I can see I've got an 8. I was going to highlight that. I've got an 8, a 2, and a 4. And it turns out that the number 8 contains all of those elements. So what I'm going to do is I'm going to multiply every single term on both sides by the number 8. And again, terms are those things that are separated by plus minus. So I can see the left-hand side has 3 terms that I have to hit with an 8. And the right-hand side has just the 1 term. Whenever I see numerators or denominators that have multiple terms in them, it's kind of useful to put parentheses there. So visually I can see, okay, that's a numerator. There's another numerator. So each one of these are going to get a factor of 8, right? I'm going to multiply it times 8 times 8. This is going to be multiplied by 8, and this is going to be multiplied by 8. And I might kind of slowly go through this and just go ahead and write, hey, 8 times the quantity of 4x minus 1 all over 8 plus 8 times 3x all over 2 plus 8 times 8 equals 8 times the quantity of x plus 7 all over 4. Now, the reason why we did that was because it allows us now to rewrite this without fractions at all. So if we look at what's happening here, the very first term, you can see I've got in this numerator the number 8, and the denominator has an 8. Right? And again, these are factors because this is 8 times something. So that's a giant 1. And it makes this first fraction just become 4x minus 1. For our next term, right, this next term, you can see I've got a factor of 8, and I'm going to divide that by 2. 8 over 2 is not 1, but 8 over 2 is the number 4. So I can choose to multiply that 4 times 3. Maybe I'll just do this. I'll say, hey, this becomes a 4 times 3x. So we can see where that 8 over 2 became a 4. And then plus 8 times 8 is 64. And then on the other side of the equation, 8 divided by 4 is going to be 2. So this is going to become 2 times the quantity of x plus 7. Okay, so if I clean up a little bit with a rewrite on the left and right, by the way, again, what did I do first right here? I multiplied everything by 8, right? Every single term got a new factor of 8. This got an 8, this one got an 8, this one got an 8. They all got 8. All right, so now let's do a little rewrite. So if I do a rewrite on the left-hand side, this is 12x. And if I combine the 12x with 4x, this looks like 16x. And then 64 and a negative 1 would be plus 63. And I can do a rewrite on the right-hand side also. If I rewrite using the simplest form of the distributive property, that becomes just 2x plus 14. So again, that was a rewrite. of both the left and the right-hand side. Now I'm going to choose to subtract 2x from both sides. So that's going to give me 14x plus 63 is the number 14. Yeah. And now what I'm going to do is I'm going to now subtract 63 from both sides. So that gives me that 14x is, and I'm using my physical calculator here. 14 minus 63 is negative 49. And then finally, I'm going to divide both sides by 14. And on the left-hand side, I get x when I divide that by 14. And on the right-hand side, I get negative 49 over 14. I'm going to consult with the on-screen calculator. What is negative 49 over 14? That gets reduced to negative 7/2. So apparently, x is negative 7/2. I'm going to circle that, but you've seen me make mistakes. I've seen you make mistakes, right? We make mistakes. So I'm going to compare that with the original left and right hand side. So let me take negative 7/2 and store that as x. So you can see if I press, hey, what's x? It says negative 7/2. That's what I told it x was. So now let's look at the left-hand side. So the left-hand side had a numerator with 4x minus 1, 4x minus 1, and the denominator, that's supposed to be an x, 4x minus 1, and the denominator was the number 8. And to that, I am adding another fraction that has 3x in the numerator. The denominator is the number 2. And then to that, I'm adding just the number 8, so plus 8. So what I get is that the left-hand side became 7/8, and my question is the right-hand side the same? So I'm going to verify that. I'm going to go ahead and grab a fraction and enter the right-hand side. You can see on screen is x plus 7. I've got x plus 7 over 4. And when I press enter, it says, yeah, that's also 7/8. So what I have here is a clean check, right? When x is negative 7/2, both sides of that equation become 7/8. So for C, our answer is negative 7/2 is what x is. X was 4. I don't know why I didn't write that down. And then our last question is another one that involves this technique of fraction busters. What's a little different when I look at this is the denominator actually contains the variable x. So I need to be careful and eliminate that as well. As I look across the denominators, I see I've got factors of 3 and I have factors of x, right? So what I need to eliminate all those fractions in one step is just a 3 times x. So I'm going to multiply every single term on both the left-hand and the right-hand side by 3x. So this will be multiplied by 3x. This will be the 3x. This will be a 3x. And finally, this will be a 3x. So let me write that out. My numerator is 3x times 12 over 3x. So that's the first purple dot. Plus 3x times 8 over x. And then plus 3x times 5 over 3. And then finally on the right-hand side, I have 3x times 5. So if we take a look at each one of these terms, right, this is a 3x over 3x, which means that side's just going to become the number 12. The next one I have, you can see there's a common factor of x over x. So this is now going to become 3 times 8, which is 24. So I've got 12 plus 24. And then plus the next one has a 3 in the numerator and a 3 in the denominator. So that's going to leave me with a plus 5x. I reordered those factors. It was x times 5. I wrote it as 5x. And then over on the right-hand side, I've got 3x times 5, which looks like 15x. Okay? So all I just did was I did a nice clean rewrite by eliminating some 1s that were there. And it was designed that way, right? We designed this entire thing to do exactly what we did because we selected this multiply by 3x. And that was exactly what we need to make all the fractions go away. They're all gone. There's not a single fraction left. On the right-hand side, we can do a quick rewrite. This is going to become 36 plus 5x equals 15x. Again, that was just a rewrite of the left side. That's all I touched. The next thing I'm going to have is a 36 is equal to 10x. I wrote it down, and what did I just do? I subtracted 5x's from each side. And then the final thing I'm going to do is divide by 10. So 36 over 10 is what x is. That is, divide by 10. And I think I can confidently say that 36 divided by 2 is 18, and 10 divided by 2 is 5. So I believe this reduces to 18/5. I don't think there's any other common factors. If you struggle with that, I want to remind you that your friend, your calculator is here. 36 over 10. Oops, not like that. Fraction key 36 over 10. And hey, one of the best things you can do is before you press enter, look at it, right? Say to yourself, what is that? Think about it. Think about it. And then, take a stab and say, I think that's 18/5, and then press enter. And if you do that, if you let your mind you're all ready to guess before you press enter, and you're going to get good at that just by looking at that and getting that immediate feedback. Okay, so what I want to do is this deserves a check, right? I've done all this work, and it would be just heartbreaking if this wasn't correct. So I'm going to take that value on my screen. I'm going to store that as x, and I'm going to enter both the left and the right hand side. So I'm going to have 12 over 3x. And I'm going to add to that 8. Whoops, Thank you. I'm going to add to that 8 over just an x. And then I'm going to add to that 5 over 3, 5/3. What's the sign of? What the? 5 over 3, 5/3. And I'm looking for the number 5 here. And I got the number 5. And what's nice about that is like, hey, the right-hand side already is 5, so I can see immediately, yes, when x is 18/5, it turned the left-hand side into 5. 5 is equal to 5, right? So that's clearly our solution. So let me go ahead and write that down. X is 18/5. All right, let's move along to the second page. This is intimidating right now for many of us. But when I look at it, I can see I've got 5, right? Factors of 5, powers of 5. I need to think about powers of 5, factors of 5. So off to the side, it's kind of useful to just kind of write some of these out. So I've got 5 to the 0 power, which is boring. That's just the number 1. I know 5 to the first is just the number 5. 5 to the second is the number 25. And that's important to me because you can see that there's a 25 in my problem. So I'm going to need 5 to the second. I could go further, like 5 to the third is 125, but I don't see any larger numbers than 25. So now I'm going to go the other direction. If I consider 5 to the negative 1 power, maybe you know what that is, maybe you don't, right? We've just talked about this in a previous problem, right? 5 to the negative 1. I can multiply by 5 to the first over 5 to the first. Right, what am I doing? This is multiplying by a giant 1. The numerator becomes 5 to the 0, which is just the number 1, and the denominator is 5. So you can see 5 to the negative 1 power is 1/5. And of course, right, it's always just a few keystrokes away. You can go, hey, what is 5 to the negative 1 power? And your calculator will tell you that's 1/5. 5 to the negative second is going to be 1 over 5 squared, or 1 over 25. Turns out I don't need to go as far as I went, right? Because the thing that I care about is this 1/5, and you can see I've got the 1/5. So here's our rewrite. I'm going to rewrite 25 as 5 to the second power. and I'm going to raise that to the 3x minus 1. So I have exactly the problem I had before, right? I just rewrote the left-hand side so that I have a base of 5. On the right-hand side, I'm going to do the same thing. 1/5 is the same thing as 5 to the negative 1 power. So I'm rewriting that base so that it looks like, I'm writing 1/5 so it looks like it has a base of 5, and it does. The last thing I'm going to do is apply this power to a power rule. So if I have a power, if I have x to the n and I raise that to the m power, that's x to the n times m. So for example, if I have x to the 5th and I raise that to the 3rd power, that's x to the 15th power. So I'm going to do that. I'm going to multiply this 2 times the 3x minus 1, and I'm going to multiply this negative 1 times the x plus 4. And when I do that, this is going to become 5 to the 6x minus 2 equals 5 to the negative x minus 4. So now that my bases are exactly the same, right, I can set those exponents equal to each other. That's the only way these will ever be true, is if those exponents are the same. So 6x minus 2 has to be equal to the opposite of x minus 4. I set it this way because I want to find the value of x that makes this true. I'm going to add x to both sides. 7x minus 2 is negative 4. And then I'll add 2 to both sides. 7x is negative 2. Therefore, x has to be negative 2 over 7. So that's what I believe x is. And of course, I'm going to check that because I don't want to leave here without knowing that this is solid. So I'm going to clear this. I'm going to say negative 2 over 7. I'm going to, I left my denominator. Sometimes it's funky storing it if you don't leave the denominator. And I'm going to now store that as x. So now my calculator knows what x is. It's negative 2 sevenths. And I'm just going to verify that it's the same. So I'm going to take 25, and I'm going to raise that to the power of 3x minus 1, 3x minus 1. So on the left-hand side, I get that decimal. I'm just going to leave that on the screen. You can see the 0.00253, etc. Now let's just look at the other side. So the other side, I've got 1/5. Great. I'm placing it in parentheses, and I'm going to raise the 1/5 to the x plus 4 power. And when I do that, I get the exact same decimal, right? So I know, right, I have excellent evidence that x must be the number negative 2 sevenths, and that's totally checked. All right, the last problem for this is, it said looking inside, rewriting, or useful strategies. When I look at this, certainly I know that the number 9 plus 7 is 16. So I know whatever this thing is, it has to be the number 9. A little confusion, I noticed that some of you were not sure about this, the square root symbol. Notice it stops right here, right? It does not extend over the 7. If it extended over the 7, you could combine that 1 and 7. But right now, that 7 and 1 may not can be combined because one is inside of the radical and the other is not. So my goal is to make this thing become the number 9, because 9 plus 7 would give me the 16. And I know, like thinking about this, looking inside, that this thing has to be the number 81, because if it was the number 81 and I took the square root of it, I would get 9. So kind of a shortcut to this is just saying, hey, this 4x plus 1 has to be the number 81. That means that 4x has to be 80, and that means that x has to be the number 20. And this one I can actually just check without the calculator, right? I can look right here. Hey, 4 times 20 is 80, plus 1 is 81, square root of 81 is 9, and 9 plus 7 is 16. So that just checks lovely. Okay, I hope you're doing well. Let's go on to question number 4. For question 4, we are given two situations that we're asked to perform a transformation. It's one of our congruence transformations. The polygons we get will be the same. They're just going to be in different locations. The first one has to do us a reflection across the line y is equal to x. And, you know, that causes some confusion. And I really encourage you, if you're like super confused by that, just get me. There's a lot of ways you can tackle this. You can say, well, let me just pick some x, y's, right? So if I was to pick some x's and figure out what the y's were, so if x was 5, this equation says that y would be that same thing, right? Y would be 5 also. If x was 7, y would be 7. If x was 8, y would be 8, right? Another way you can look at that is, hey, this is y equals mx plus b. The slope of this is 1, or so I could say up 1 over 1, and my y-intercept is 0, right? So we're reflecting across a line. This line is not the x-axis. It's not the y-axis. It's the line y's are equal to x. And that line goes through these spots, right? These spots. So I need to reflect across those lines. A couple things we remember from earlier on in the chapter is that when I do a reflection, right, the image that results is going to be the same distance from the line that I'm reflecting across. So that's kind of an important idea. I'm grabbing a physical ruler, putting it on the screen. I'm trying to draw, oh no, trying to draw that line. That's terrible looking. Maybe I'll have to use the electronic ruler, but let's just go with that one for now. So I can, the slope of this line is up 1 over 1. So the slope of the line that connects these original points with the image points is going to be the slope of a perpendicular line. So I'm going across slopes that would be opposite reciprocals of 1, which means it's just 1. So this, right, that's 1, 2, 3, 4. And it's actually not the number 4. That's 4 times the square root of 2, but I don't care about that. It's just 4 of those units. And I could extend that 1, 2, 3, 4 more units. What I get is that this location right here is where A prime is going to be, right? So after that reflection, A prime is going to land right there. Same thing with the D. That's like 1.5 of those square roots of 2. There's a root, half a root 2, and a root 2. So D is going to land at this location. There's D prime. B, 1, 2, 3, 4, 5. So I'm going to keep counting. 1, 2, 3, 4, 5. This is going to be the location of B prime rather. B prime. And then the last one is this C. 1, 2, 3, 4. 1, 2, 3, 4. So C should land right here. And there's C prime. All right, so I use that ruler and connect those points, but this is where this should land. And I didn't ask you to identify the coordinates of any points because I was checking all 4 of them, but that is basically what happens when you reflect across the line y is equal to x. The next problem asks us to do a rotation. I think it says 90 degrees clockwise. So I'm here and I'm going to have to rotate 90 degrees this direction. And my favorite technique for doing is to consider these little L's. So I've got this little L right here. And if I look at that, it's kind of I'm making slope triangles back to the origin. So I'm like going up 1 over 3. So if I wanted to rotate that 90 degrees, it has to be, right now it's up 1 over 3. But if I was going to do this, it would have to be the opposite reciprocal. So it would have to be negative 3 over 1. And what I could do is I could go, up 3 units and then backwards 1, right? So this little L that I've just drawn, right, that's exactly the shape that I would get if I was to rotate that original L 90 degrees. The significance of that is exactly where point C lands, right? So this is the location of C prime. And I can do that with a bunch of these little L's. Let me let me erase that and do another L for B. So you can see this is like up 2 and then over 6. So instead I could go up 6 and then backwards 2. So what I have now is this new location for B prime. And again, it's just observing the fact that I'm doing 90 degrees, and whenever I rotate things 90 degrees, I get perpendicular lines. And we have perpendicular lines if our slopes are opposite in sign and reciprocals, opposite reciprocals, opposite reciprocals. So again, I could play the same game with A. From here, from A, I would go, let me use this, I'll use this cosmic color. I'll go up 3, right? I go up 3, then I go over 6 to the right. So that's up 3 over 6. So going the other way, I'm going to go up 6, and then I would go backwards 3. So that point right there would be the very beautiful point where A prime lands. And again, you can see, when you're looking at those L's, it's really easy to imagine, like, yeah, that shape totally rotates 90 degrees and lands where I think it does. And I got one more of those. The last one down here is for D. It's a little bit different. I'll use the cosmic, whatever pen this is. I'll go back 1 and then, or actually from the point D, I would be going up 6 and then over 1. So that's a positive 6 over 1. So now I'm going to go up 1 and backwards 6. Up 1 and back 6. So that point, right, is where the point D lands. Now, what's beautiful, right, is you guys know you can come up with very nice transformation rules that involve X and Y and that transformational notation. I really encourage you to think about that, especially if you're in a situation where you're writing a program and you need to do this for a bunch of points, right? We don't sit here and think about each of these points like this. We come up with a rule that we can apply quickly and efficiently for all the points. And but let's go ahead and just draw this shape. So here, I'm just kind of sketching this now. By the way, thank you for using rulers on your test. Please do that on Friday also. All right, so that's the shape that we get when we rotate that thing 90 degrees clockwise about the origin. For question 5, we were given 2 very nice functions and asked to use those to evaluate a couple expressions. One of the functions was this function g of x, and the definition for g of x is that it's equal to 3 times the input squared minus 2 times the input and then plus 5. So you can see that's the definition. And for part A, it says, hey, what does that become if I give it an input of 3? So if I want, I could write, hey, here's 3 times the input's going to get squared minus 2 times the input and then plus 5. When I place the number 3 here and here, right, that's the input into the function 3, I get 3 times 9 minus 6 plus 5. 3 times 9 is 27. And negative 6 and 5 is a negative 1. So we get 26 is the output when we feed the number 3 into that function. 26 is the output. The next one says, we're going to use both functions to evaluate an expression. This one says that we're going to feed the function f, the number 10. You can see the definition of f. It's pretty straightforward. F is defined as just whatever the input is divided by 2. Oh, I could do that. Let's do that right now. So if 10 goes in there, this is going to become 10 over 2, or it's just going to become the number 5. So f of 10 is 10 over 2, which is 5, plus we need to add to that whatever we get when we feed 2 into the function g. So let me go ahead and do this again. G is 3 times some input. The input in this case is the number 2 minus 2 times an input of 2 and then plus 5. So we're looking at 3 times 4. I square first, so 3 times 4 is 12 minus the number 4 and then plus 5. And that's going to become 12 plus 1, or 13. So what we're looking at here is g of 2 is the number 13. And when we combine those two, we get the number 18. So part B, the output or the result of f of 10 plus g of 2 is the number 18. C says that you're going to take f, feed 20 into it, and then you're going to do something to that result. So look, I'm going to write it's a half times what we get back from f when we give it the number 20 plus 5. Well, we know if I send 20 into f what it does, right? It takes that 20 and divides it by 2. So you can see what I've got here is 20 divided by 2 is 10. I'm going to take a half of that again and then add 5. So half of the 10 is 5 plus that 5 more gives us a final output of 10. So 1/2 of the output of the function f when you feed it 20 plus 5 more is 10. Ugh. I'm reading it, right? It says like 1/2 times, this is the output of the function f when you feed it the number 20 plus 5 more is 10. All right, and the last question there says you're going to feed something to g of x. Something's going to go to g, but what's going to go to g is whatever you get when you feed 2 into f of x. So I'm going to feed the number 2 into f of x, and that's going to be 2 divided by 2 equals 1. So f of 2 is 1. So here's the thing. This is going to become g of 1, right? So we're going to ship off the number 1 to the function g and evaluate it. If I do that, remember g is just 3 times the input squared minus 2 times the input plus 5 more. The input is 1. So I just get 3 minus 2 plus 5. 3 minus 2 is 1, plus 5 is 6. But I got a problem. Don't forget, there is a 10 here, right? Don't forget this 10. So I end up with 6 plus 10, which gives me the number 16. So 10 more than g of f of 2, or 10 more than the answer to g when you feed it. The answer when you give f2 is 16. All right, moving on. Question 6. It says, find the equational line that goes through the points. Okay, this is kind of one of the key questions for this chapter, right? You should be able to quickly and efficiently come up with an equation given a couple of points. I'm going to go through and calculate the slope. So I'm going to write -6 minus 30. So what I've just written down here is the difference in my y values. And then the denominator, I'm going to take -8 minus a -10. So if you look what I have here is I took the difference in my x values, and I did the same order for those points. This numerator is the number -36, and that denominator is the number +18. So we're looking at -36 divided by +18. And I'm going to say I don't need a calculator. That is -2. So my slope is -2. And I have to write the equation of the line. And you guys know I've been talking about point slope form. I'm very happy if you use it. So there's a lot of things I would have accepted as answers. If I was going to use the first point, I'll write the answer in red for the first point. You could have written y minus 30. That's y minus the y value that I know equals my slope times the quantity of x minus -10 or x plus 10, right? X minus 10 is x plus 10. So that's one acceptable answer. Point slope form where you're using the slope of -2 in the first point. Also an acceptable answer. You could have used this point and written y, let's see, minus the y that I know. So y minus -6 would be y plus 6 equals my slope times x. And then in this case, it would be -10. No, x minus 8. I'm sorry. minus 8, because the x value that I know for this point is 8. And that would have been an acceptable answer. For both of these, if you were to get y alone and distribute the -2, both of them get the exact same y-intercept. Like if I was to modify this equation by adding 30 to both sides and distributing the -2, it would become -2x minus 20 and then plus 30, which simplifies y equals -2x plus 10. So this is another acceptable answer. That's the y-intercept, slope-intercept form. And just for fun, if I was to do the same thing here, this would become y. I'm going to subtract 6 from both sides. So this is going to be y is -2 times x plus, let's see, -2 times -8 is plus 16, and then subtract 6. So again, I'm distributing this -2 to both of the terms, and then I'm I'm subtracting 6 in this case. But notice, what does this become? Right? It becomes exactly the same thing. Y is -2x, and then -16 plus 6 is plus 10. Positive 16 minus 6 is positive 10. So lots of different things I would accept as answers. Clearly, this point, this box in red is a valid answer. That's point slope form using the slope we found and the first point. This is point slope form using the slope we found in the second point. And then these are both y-intercept form, and they're identical to each other. And that's just a matter of rewriting that equation. All right. One thing you could do too is, if you're curious, like, geez, did I get this right? How do I know if I'm correct? You could check these answers by plugging in, I've got a laser point. You could plug in this x into x here and verify when you do that, that the y, right, becomes -6. And you can also plug in that x is -10. And when you plug x is -10 in to that equation, it should be the case that it forces y to be the number positive 30. So plugging in your x values and confirming that you're getting the correct y is a nice way to check the validity of your equations. Question 7 says, find the equation of a line that goes through the point 8, 10 and is perpendicular to the line y is equal to -2/3. So I was a little surprised to learn that some of us were unfamiliar with the word perpendicular and this idea of what happens when you rotate things on the plane 90 degrees clockwise or counterclockwise. So if I was to just quickly sketch the line, I'll just do the line y is equal to -2/3 x, and then we had -7. Okay, so this is the line that we have, and we're being asked to come up with a line that goes through a particular point. It has to go through the point at 8, -2. So we're looking for a line that's going to go through this point right here. I think I can draw on this. Tools. Can I draw? No, I can't draw. Well, I can, but I don't. But it's this point. I can type it. I can type 8, -2. So we're being asked to find the line that has two properties, right? One of the properties is it has to go through this point. It has to travel through this point, and it has to meet this line at a right angle. It has to be perpendicular to it. And anytime I have slopes that are opposite and reciprocals, so it switches the plus minus and the numerator and denominator flip, I'm going to get right angles. So for example, if I was to just quickly graph the line below that, I'll graph y equals +3/2 times x. Notice what happens here, right? These clearly, right, are forming a right angle. You can see it visually. It's compelling. And I can also demonstrate this with a rotation. But unfortunately, that's not the answer, right? I need it to hit this point A as well. So what we need to do is we need to figure out that equation. So if we go back to our problem on the test, we know that the slope that we're going to be using, because it has to be perpendicular, oops, let me grab the pen, because it has to be perpendicular, our slope is going to be positive 3 over 2, right? I can see before the slope was negative 2 over 3, so I'm flipping it, making it positive 3 over 2, but it also has to hit this xy value, right? It has to hit those. So I can type the equation of that line in point slope form. So I know y minus 10 equals 3/2 times the quantity of x minus 8 would totally do exactly what I need, right? It would form a right angle with this line, and it would pass through this line. So let's go ahead and see if we can observe that in GeoGebra. Oops. So I'm going to go ahead and type the y is equal to, or I'm sorry, not equal to, y minus 10 is equal to 3/2 times the quantity of x minus 8. I have a problem here. Y minus 10 equals 3/2 times the quantity of x minus 8. Close parentheses, enter. Oh, yeah, I know what my problem is. My problem is the test didn't ask me to come up with a point that went through 8, negative 2, right? The test says come up with a point that goes through 8, 10. So I'm sitting here shocked that what I just typed didn't go through this point A, but it wasn't supposed to go through that point A. It's supposed to go through the point where x is 8 and y is positive 10. So let me put 10 there, and boom. So now we should see, yeah, there we go. So this red line is exactly what we're looking for, right? It is the line that's perpendicular to our original one, and it's exactly hitting at the point 8, 10. So such a nice tool set. So cool to be able to do that. Of course, I can take that equation and I can rewrite it in slope-intercept form by just distributing the 3/2 and adding 10 to both sides. And that would be y is equal to 3/2 times x and then minus 2. So you see, I'm getting the exact same result there. But now there's an orange line that's showing that. Cool stuff. All right, so this, of course, is a totally valid, acceptable answer. That line is written in point slope form, y minus my y value, y minus my known y value, right? The known y value is 10, equals slope times the quantity of x minus my known x value, which was 8. Again, I could distribute the 3/2, so this would equal 3/2 times x, and then 3/2 times negative 8 would be, I believe, negative 12. 8 divided by 2 is 4, yeah, negative 12. And then 2 that I'm going to add 10. So y is equal to this. So I could also change that to y is 3/2 x and then minus 2. So either one of those would be perfectly acceptable answers. All right, we're getting very close. We're on the last page. You can see me going slower like this would have required more time than class time. So I apologize that I had to go through this so quickly in class, but I hope you found this more helpful. And of course, watching several times, making sure you understand what's going on. And at the end of this video, I'm going to show you a place where you can go get some more practice that I've created just for these concepts. It's not in Delta Math, it's a different place. So hang on till the end. So for this last page, the first question says, hey, express the area of the rectangle below as a product of its dimensions equal to the sum of its parts. So I spelled that out. The product of its dimensions is I need to see what's its length times its width equal to the sum of its parts. Well, if I look at this, the length, I guess I could call it, this is x units long. So I've got x, and these are each 1 unit long. So this is x plus 3, x plus 3. And I'm multiplying that by 3x's plus 2. So I'm multiplying that by 3x plus 2. And when I multiply those, right, I get the area of the rectangle. And the area of the rectangle expressed as the sum of its parts is I've got 3x squared, right, 3x squared. I've got 2x's here and 9x's here. So that's a total of 11x's. So plus 11x's. And then finally, I have 6 units. So 6 plus 6 ones, or plus 6. So, at this point, I easily expect that if I gave you this and I ask you to multiply it by this, you would be able to create, a generic area model and come up with the product would have to equal this. All right, last question involves quite a bit of graphing. It says, carefully and accurately graph the following 5 lines. Use a ruler to create accurate lines and label each line with the listed letters. So the first one starts out here with a slope of -2 and a y-intercept at 7. So I'll use red for this one. I'm going to begin at 7, and if I have a slope of -2, that's going to be down 2 over 1, down 2 over 1. And I'm just going to extend this down to back 1, down 2 over 1, down 2 over 1, down 2. All right. So those red dots, boy, feels like I switched it up. Those red dots should represent A. So I'll write a letter A there in red. The next one says graph the line where x is 9. And this caused some consternation for some of us. But the more you look at it, it's just like, okay, points where x is 9. Well, here x is 9, right? In fact, y is 0. Y is 0, but x is 9. Are there any other points on the Cartesian coordinate plane where x is 9? It turns out, yeah. Oh, what are you doing? Yeah, well, it turns out, yeah, there are. In fact, this point, x is still 9, but y is 1. Up here, x is 9 and y is 6, right? X is 8. I'm sorry, y is 8, but x is still 9. Guess what? Y is now -3, but x is 9. So all these points on that vertical line are part of the line x is 9. So this is my answer for B. I'll draw the lines at the end. The next equation, this is written in point slope form. So I know just by looking at it that this has to go through the point where x is 3 and y is 5. So, because if you think about it, the formula is y minus your known y value, so y minus +5 equals your slope times x minus your known x value, so x minus +3. So I know that this is going to pass through the point, I'll use blue, where x is 3 and y is the number 5, right here. And it has a slope pattern of up 2 over 3. So from here I can go up 2 over 3 units. I just ran out of room that way. So I'll go down 2 and backwards 3, and then down 2 and backwards 3. So that's going to be another line that I draw, and that's going to be line C. I'm saving all my line drawing for the end. D, there's 2 strategies I could go with. I could definitely solve this for y, and I would have it in slope-intercept form. But it's also written in standard form, which is you can graph pretty easily by just observing that this is an easy way to get your intercepts. So for example, my intercepts, one of them is where x is 0, you get your y-intercept. And the other intercept is where y is 0, and that's when you get your x-intercept. And if I was to play the game, I could say, look, I want x to be 0. Right, so I cross this out, x is now 0. There's no x. And if I look at this equation, it says 4y is 12. Okay, if x is gone and 4y is 12, if I divide both sides by 4, I get that y is the number 3. Right, so when x is gone, y is 3. And then I could play the same game with my to find my, that's my y-intercept, but I could find my x-intercept. My x-intercept occurs when y is gone, so there's no more y. If I divide both sides of that by 3, I get that x would be the number 4. So these 2 points right here allow me to pretty quickly graph that line. When x is 0, let me use purple. When x is 0, y is 3. That's this point. And then when x is 0, when x is 4, y would be 0. So these 2 points are my intercepts. I've got the y-intercept up here at 3 and my x-intercept here. So, and that slope pattern is down 1, 2, 3 over 1, 2, 3, 4. 1, 2, 3 over 1, 2, 3, 4. But with a ruler, I should be able to draw that just fine. And then the last one we have, let me go ahead and add those lines real quick. I did go through and add all of those lines, and of course I should have some nice arrows indicating that these are infinite creatures that go on forever in all directions. They got things to do, places to go. Let's let them go to those places and do the things that they're going to do. We'll never be able to travel with them because they move too fast and the distances are too far, but good luck, lions. We'll see you later. All right, but we got to see what happened at the origin right here. We saw at the beginning what they were doing. All right, the last one says, add a final line to this graph that is perpendicular to line C. Okay, here's this word again. Perpendicular to line C. I can see C is in point slope form. It has a slope of 2/3. So if I want to be perpendicular to C, right, 2/3 is going to become -3/2 if the lines are perpendicular. This upside down T is the symbol we use for that word if they're perpendicular. So, and it has to pass through this point where x is 8 and y is -2. So let me grab, I need a new color. I'll use this thing. There, I'll use the Fiesta color. So at 8, -2, I have this point. Okay. And my slope is going to be down 3/2. There we go. And I can extend that the other way by going up 3 and backwards 2. Up 3 and backwards 2. So you can see those points lining up there. If I get my ruler and line it up. Okay, come on, ruler, do line up. Don't embarrass me. And then I just draw that line. And that is our final line. This is line A, B, C, D, E. And it needs to have some arrows also. All right, so there you go, right? That's the entire test. Let me know if you've got any questions or any help that you'd like. So where can you get some extra practice? Let me show you this. So I'm going to include a link to these problems, probably in Google Classroom, but it says Chapter 3 Tough Practice. I don't know what that means, but I've got quite a few problems here. And this is a form, and this is set up so that when you enter one answer, it's going to show you right away if you were correct or incorrect. I just want to caution you that your answers, if you want them to be counted as correct, this is not a quiz, this is just for your own information. The answer should be simplified fractions, not decimals. If the fraction could be reduced, it should be reduced. So if it's a fractional answer, make sure you give me a clear numerator or over a denominator. And there's a bunch of these here. And then you just hit submit and it'll give you the answer to that one and take you on to the next one. There's 17 of them and I might be adding more. Just be aware that if you have a fraction that you type in your answer and it's a fraction that you didn't reduce, you're not being penalized. It's just questions for you to do and then check. But to be honest, right, before you submit, you should practice checking to see that your answer is correct, right? So anyways, there's 17 questions here. Some of them involve just simplifying monomials. Some of them involve solving using fraction busters or looking inside, or that trick we have to do with the rewriting the bases so that the bases are the same, and then setting the exponents equal to each other. All right, guys, I am in room 309 if you need assistance and want to talk about any of these things. Feel free to get in touch with me, and I look forward to seeing you in class.